In this video, I'm going to do an example that uses Stoke's theorem. So let's first try to sketch the region that we're talking about and see how and why Stoke's theorem might apply. So what we have is some particular half sphere, x squared plus y squared plus z squared equal to 1, but only the portion which is greater than 0. So I'm going to go and sketch a half of a sphere. And then through that surface, we have this vector field y in the I hat, minus x in the j hat, and z in the k hat. Just some vector field. Doesn't matter too much for the purposes of our story here. Now, I actually have to tell you one more thing in the example, and I'm going to tell it to you pictorially. I have to tell you an orientation for the surface and for the boundary curve that should be compatible with each other. So what I'm going to imagine is the boundary curve is rotated around this way in the counterclockwise direction when viewed from above. This is compatible with having our normal vectors to the surface be pointing outwards at any particular point, and that satisfies the right-hand rule that when you take your fingers and go along the boundary, the normal would be sticking upwards. So that's my choice of orientation, and I'm going to impose that as part of the problem. Now, Stoke's theorem is an equality between two relatively different things. On the left-hand side, it's the circulation around the curve. So maybe I'll just take the base curve and I'll draw it in on blue here to indicate that's one question I could ask. What is the circulation around that curve? The other question I could ask would be to integrate, well, the curl in the normal direction, the curl of f dotted with n, and integrate that over the entire region. So a surface integral, that would be something I'd be doing over the entire region. Now, often one of those two things is easier and the other is going to be harder. So the types of problems you might use Stoke's theorem for are often when one of these is doable and the other is not. In this example, actually, both of them are going to be doable, both sides of this equation. So I'm really going to use this example to make sure I can do both sides of the computation and then note that they are indeed the same as Stoke's theorem is going to get us. And then we're going to have a really cool point at the end where we say, well, hold on, I could even replace this surface with a completely different surface that still has the same boundary, and we'd get the same result there as well, but it will be just vastly easier. Okay, so which side should we do first? How about the left side, the circulation? The question of what is the circulation along this boundary curve of this field is a problem we could have done back earlier in the course. And indeed, the most important thing is to come up with a parameterization for the curve. So I'm going to do that. I'm going to have a parameterization for that boundary curve. I'm going to parameterize it into theta. The boundary curve is just this unit circle, and so I'm going to write this as cosine of theta with radius 1 in the I hat, sine of theta in the j hat, and then 0 in the k hat because that boundary circle is in the xy plane. It has no k hat component. The next thing I need to do to compute a flow integral or a circulation integral like this is to compute the derivative. So I'm going to compute r prime of theta, and I'm going to get minus sine of theta in the I hat, cosine of theta in the j hat, and still 0 in the k hat. So now I'm actually going to compute that line integral along the curve of f dot dr, having established my r and my r prime. And what this is the integral from 0 up to 2 pi. I, by the way, added in that the theta values were between 0 and 2 pi, as you should always tell the endpoints of your parameterization as well. Okay, so then what we're going to be integrating is the field f dotted with r prime dt. And so what I have is my field components. Well, the first field component is y, which in this parameterization is sine of theta. So we sometimes call that the m if the field is written in m, n, and p components. Anyway, sine of theta times the minus sine of theta, the I hat component of my r prime. Then to that I'm going to add the minus x, which written in terms of our parameterization is going to be minus cosine, so minus cosine of theta, that is our n, multiplied by the j hat component of r prime, which is cosine of theta, and then plus 0 because the r prime has 0 in the k hat, so I'll just come there and put in my dt. Minus sine squared plus minus cos squared is just minus 1, and so this is going to be minus 2 pi. All right, so there's our result for the circulation minus 2 pi. Not so bad. So if I scroll back up to Stoke's theorem, that was the left-hand side, but I also want to do the right-hand side, and I'm hoping that I can do this and also get the value of minus 2 pi. And I'm going to have to do the curl of f, and then I'm going to have to dot it with n and then take a d sigma. So working from the inside out, the first thing for me to do is figure out my curl of f, and then I'm going to go and dot that with the normal vector, and I'm going to have to figure out what both of those things are going to be. All right, so let's do that computation. The curl of f is equal to the determinant of I hat, j hat, k hat, then the partial with respect to x, the partial with respect to y, and the partial with respect to z all goes along the second row, and then finally the components of the field f itself, y minus x and z, go in the third row. You'll notice here that I'm not memorizing the larger formula for the curl that we've introduced. I'm preferring to think of it in the determinant way. This is perfectly fine for all the computations that I'm going to be doing. Okay, so I hat component first is going to be the partial with respect to y of z, 0, the partial with respect to z of x, which is 0, so just 0 in the I hat. The minus j hat is going to be the partial of x with respect to z, again 0, the partial of z with respect to y, again 0, nothing there as well. And then finally I'm going to have a k hat component. I think that's non-zero, thankfully. So the k hat is the partial with respect to x of minus x, which is minus 1, minus the partial with respect to y of y, so in other words, another minus 1, this is equal to minus 2k hat. The next thing I have to do is compute the normal vector, and as we've seen when we're doing surface integrals before, there's actually 3 different ways that we might want to try and approach this issue of the normal vector and the d sigma. We could do it parametrically, implicitly, or explicitly. I have an implicit formula here, x squared plus y squared plus z squared equal to 1. And so I'm just going to use the implicit formula that the normal is the gradient of g divided by the length of the gradient of g. I should be precise by what do I mean by g. Let's go all the way back to the beginning. I'm calling the g all of that, the x squared plus y squared plus z squared, so the surface is g is equal to 1. Now I actually sometimes find this easier to go and deal with the normal d sigma all in one go. It's has a little bit of cancellation to do the normal and the sigma together. That's true for each of parametric, implicit, and explicit. So if I do this, then what I would be getting would be the gradient of g divided by the length of the gradient of g dotted with k hat, and then a little element of area. The shift from a little element of surface area, d sigma, to dA has this stretching factor, the magnitude of the gradient of g divided by the magnitude of the gradient of g dotted with k hat, because the surface is in the xy plane and the k hat's just pointing straight up. We've seen that the length of the gradient g just cancels in both cases. It's just easier to go to this formula directly. Okay, so let's actually do that computation then. So the gradient of g is the vector 2x, 2y, and 2z. The gradient of g dotted with k hat is just the third component of this, in other words 2z. So I'll divide out by the length of 2z, and then I'll still multiply this by the dA. Alright, so now I think I'm finally in a position to come forward and write out my surface integral of the curl of f dotted within d sigma. And multiple things are going to be happening in this formula at once. So the first thing is, it's going to be a double integral over the region now. So this is the region in the xy plane, where I'm thinking of my surface being above it. That is, I'm shifting from a d sigma to a dA here. Then I need to execute the dot product between the curl and this expression that I just had. So I need to remind myself what my curl was. So if I go up a little bit, I'll remind myself that my curl was minus 2 in the k hat. All right. So then here, the only k hat component is the 2z. So what do I have? I have a minus 4z. That's the dot product between the minus 2 in the k hat and this 2x, 2y, 2z, all divided by the length of 2z multiplied by dA. And I still haven't figured out what the limits of my integration are. I'll do that in a moment. And then now it's just a computational question. This integral here is, well, let's do it again. The double integral over the region, minus 4z divided by 2z. Z was always assumed to be positive, so I can drop those absolute value signs. It's just going to be a minus 2 times dA. And, well, what is the region? So if I scroll all the way back to the beginning, the region was the portion above the circle of unit 1. So in other words, it's a circle of radius 1. It's got an area of pi r squared. So if I come all the way back down, well, I don't even need to bother writing limits of integration here. It's just the circle of radius 1. So the final answer is going to be minus 2 times the area of that circle, which is pi r squared. R is 1, so just pi minus 2 pi. And thank goodness we've gotten the exact same answer that we had before. So indeed, we've gotten the same answer using both sides of Stoke's theorem. One, computing the circulation directly, and secondly, doing a surface integral of the curl of f dotted with n. Now, I want to do one final thing here, and it's kind of a cool little trick in the exact same example. So my setup was I had this circle down in the xy plane, and then my choice of surface was the hemisphere above it. However, if you have two surfaces, they both have the same boundary, but the surfaces are completely different, then the surface integral of curl of f dotted n over the first surface and the second surface have to be the same, because they're both equal to the circulation on the boundary. And so if they have the same boundary, they also must have the same surface integral. So what would be a simpler surface to deal with? What if instead I'm going to get rid of the hemisphere, I'm going to keep the boundary being the exact same thing here, let's close it up for my erasing. What if I made my surface be just the flat disk? That's a pretty easy surface. In fact, it's a very easy surface because we can do almost everything about it. For example, if I want to figure out that normal vector now, the normal vector is just k hat if I use a flat disk. And so, well, let me try and do my surface integral now of the curl of f dotted with n. Well, we've already shown that the curl of f was just minus 2 in the k hat direction. So that's what the curl of f is. Dotted with k hat, so that's going to be my normal. Oh, I forgot my d sigma here. And then integrated with respect to area, and I'm going to put down here the region again, which is just the circle in the plane, circle of radius 1. The dot product is easy enough, so it's the double integral over the region of minus 2 dA, and I know what that area is, it's just pi r squared, r is 1, so it's just pi minus 2 pi. And so we get the exact same answer a third time. So previously, when we thought of Stokes' theorem, we had these two different portions of it, one for the boundary, one for the surface, and basically, depending on what you're interested in, which of those computations was easier, you might do one side or the other to get the opposite side. But now we're really opening it up, because you don't have to use the surface that you're given. You could compute it via a completely different surface as long as it has the same boundary. Indeed, you can just make the easiest surface that you can imagine. So for example, any time when you've got a planar curve, so a curve that's just in the xy plane, it often makes sense to have, as we just did here, the surface be just the flat region inside of that curve in the xy plane. Not always, of course, it would depend on the computation. But the point is, if you can replace the surface that you have that's messy and maybe you don't know how to do the surface integral with the surface you have, replace it with an easier one, you can sometimes gain a really big computational advantage.